7.4 has us stray just a little bit from our nth roots and our power functions to add in inverse functions. And it might seem initially that this kind of is out of place, or what does it look like? But as we move on and we are looking at our root functions and comparing it with our exponential functions, we can see that they're really just two sides of a coin. So we're flipping back and forth. And it's important, as we have learned all along, that when we know something from before, it's still valid as we move forward. And there's really not a lot of brand new things. It's just shifted to a different form or a different direction. And we can use all of the same tools from our tool belt previously to move forward. So these inverses do help us because everything has an inverse, right? At the very beginning of the year, we talked about our different properties. So we had the commutative property, we had the associative property, we had the identity property, and we had the inverse property. So remember, our identity made us look like ourselves. So it's going to reflect back exactly what was in the mirror. And our inverse property got us to the identity. Because our identity doesn't change anything. That was the whole point that we learned back at the very beginning of Algebra 2 when we were going back over that, is that when we are having addition, and if we are adding the identity of 0, then it doesn't change it. So we get back what we started. If x is on another side, we're going to get it back. On the what's on the left side is the same on the right side. When we were using multiplication, we know that our identity for multiplication is the number 1. Because when we multiply times 1, we get the same thing back. It's still going to be x on that side. So these are important as we move forward for inverses. So let's just think about, I wrote down here that typically we think of an inverse as positive versus negative. And when we are having a number line, it is. Because if I have 4 on one side, my inverse is negative 4. So 1 was positive and 1 was negative, right? And it's flipping and rotating around this point of 0. So if I folded this paper in half, these 2 points would line up exactly if I just fold over and make my line match, because all I'm dealing with is the number line. For multiplication and division, that inverse was the term that produced the number 1. So if we have 4 again, so in this case, negative 4 and 4 are our additive inverses. But then if I have 4 for my multiplicative one, I have to have 1/4, because 4 times 1/4 gives me the number 1. It doesn't change anything. So it gives me that identity, okay? And that's important to know where your identity and where it's going to lie. Okay, so when we have a function equation, our inverse, just like when we had matrices, back at matrices, we had a matrix, and then we had an inverse matrix. And the inverse matrix, when we multiplied them together, always gave us the identity matrix. So every time we've worked, whether we've worked with addition and subtraction, whether we've worked with multiplication and division, whether we've worked in matrices, or if we've worked in functions, we're always ending up with this identity over here. Okay, so if I have a function, my inverse is some other equation that must produce the identity. It must produce it. That is the whole key on which this lands, is that when I add these together, I got 0. When I multiplied these together, I got 1. It must produce the identity. for it. So then we have to ask ourselves, now that I'm dealing with functions that are not just numbers on a number line, what is the identity? Well, we knew that the identity is the thing that reflects itself. It's what it's in the mirror. So now that I'm dealing with functions, which means a line, a parabola, an S-curve, some sort of equation that lies outside of our number line, it's now encompassing the entire coordinate plane. Where would I find a line or something that would reflect or produce itself? And we find that in the line of y equals x, which means that whatever I put in for x, I'm going to get out for y. So if I were to have a chart, I would have the same thing on both sides all the way down for infinity. And if I fold them in half, they're going to meet and they're going to match, because here's my mirror. My mirror is right in the middle. So what I place on one side is reflected what I place on the other side. So this makes the line y equals x our line of reflection, like a mirror reflecting an inverted image. So when it hits this line, it's bounced back to the other side and your inverse is revealed. Okay, so we write our inverse as f to the negative 1 of any function. So if our function is f, then our inverse is f to the negative 1. This should look very familiar because in matrices, we had matrix A and its inverse was a to the negative 1. We also talked about the reason that if we have 4, then 4 to the negative 1 is really 1 over 4, because we are changing sides to change the sign, and that gives us our inverse. So not a new notation, it's the same in all things, and it comes from that exponent power there. Okay, and so I just explained that. So then what does it look like when we have this line of reflection, y equals x? Well, everyone should know that y equals x. I'm going to pull this up. Y equals x is our basic 45-degree angle. That means if x is 1, then y is 1, and I would have a new point. Here I have x is 4, y would be 4. X is 6, y is 6. X is negative 2, y is negative 2. So the thing that changes about this is that when we are dealing only with the number line, we are reflecting around our 0, so that our number line itself is lying on top of itself. Or we could do it this way. We could fold it in half so that our number line is going to meet all the way there. And that works great when we are only dealing with numbers along our number line. Now that we are dealing with our entire coordinate plane, our mirror line of reflection is now this diagonal line, y equals x. So that is going to change how things move on the page. And we're going to use some papers to visually see that so that we can start wrapping our head around the fact that we are not looking left to right, and we are not looking top to bottom. It's not reflecting straight like that. It's reflecting on a diagonal line. And so we have this coordinate plane, and we're going to fold it right along that diagonal so that it matches right there. So here is our line of reflection. And as we plot points, we're going to use hole punches or a sharp pencil so that we can see exactly where it looks like. So we're used to looking at our coordinate plane perfectly up and down and left to right. To look at our line of reflection, it may be helpful to turn your coordinate plane Since our bodies like symmetry, left to right, to turn it where your line of reflection is now your vertical line, and you can see from one point on the left, and it's going to be moved over to a point on the right, and vice versa. Okay, so before we start plotting that, let's talk about how do we actually find that inverse in the first place. So we find inverses with one simple step. So we typically might have y equals x plus 3. To find the inverse, it means that where y was is now x, and where x was is now y. So all we do is switch them. X is now equal to y plus 3. Now, we don't like solving equations for x. So we take our new equation and we solve for y again. So in this case, y is equal to x minus 3. So where my first function here is x plus 3, my inverse function is x minus 3. And this one looks easy because you say all we did was just turn our y values or our constant over here negative. It doesn't always work that way. So, but that's what we do. We're just going to switch our x and y. And so for the inverse to be true when we're talking about functions, remember what did we say? It must produce the identity. Correct? And so what is our identity? Well, if our identity is y equals x, then as we do our functions, we've got to come out with an x over here. Okay. So our check with that, just like we say for addition, we actually have to add them up to see if they produce the identity. For multiplication, we actually have to multiply them to see if they produce the identity. For matrices, we had to multiply them to see if they came out with the identity matrix. Correct? So in the same way as we have two functions, we have to know that we use that composite form that we just learned in 7.3, that when we do f of g of x, it has to equal our identity x. And this is a really important part, and when we swap them around the other direction, g of f of x also has to produce the x value. If one of them produces our identity x and the other one does not, they are not inverses of each other. Okay? So don't let it feel super complicated. Just know that when we are combining both functions, we're just getting that identity value of x. So let's look at that practically. So practically, I have these two equations. I've got y equals 2x minus 4 and y equals 1/2 x plus 2. And I'm telling you, they are inverses. Okay? How did I find out that they got an inverse? Well, I'm going to take this first one, y equals 2x minus 4. And to find my inverse, I simply need to swap them. So instead of y equals 2x minus 4, I now have x equals 2y minus 4. Again, we can't graph a line by x, so I'm going to solve for y. Move 4 to the other side, divide by 2, and I have y is equal to x over 2, or 1/2 x, plus 4 over 2, which simplifies to 2. So now I have these two equations, so I get to graph them, and I'm just going to check just to be sure. So we know that our line of reflection is that 45-degree diagonal line is where we're going to go. So our first one, y equals 2x minus 4. So I have an intercept down here of -4, and I have a slope of 2. So I'm going to go up 2 over 1, up 2 over 1, plot several points, and draw myself a line. So for my second one here, I've got an intercept of +2 and a slope of 1/2. So up 1 over 2, up 1 over 2. Now, they should cross on the line of reflection. Okay, so if they meet and they cross anywhere else other than the line of the reflection, then they haven't been graphed appropriately. And what I'm going to do instead is I am going to take this and I'm going to turn it where my line of reflection is vertical. So now my line of reflection goes straight up and down. And if I were to look at this and say, because we get caught up with our y-intercepts being in different places. But if I were to look across here from my point, sorry, to my line, I go across one diamond. And then from my line of reflection to the graph, I go across one diamond. So these two are the same distance from the line of reflection. Hold on, let me get some water. In the same way, I can look down maybe at some other points. And I can see, now that I have turned my graph where my line of reflection is my vertical point, that my points are equal distance from my mirror right here in the middle. So two different lines, but our graphs are inverses of one another. Okay. Let's look at another one. So there's several different ways that we can check. We can check it with that fold test. And then, which that's what we were just doing, we can also check it with our math function test, because it tells me that f of g of x and g of f of x must equal x. They must both produce that identity. So I'm going to take my two functions. I'm going to take label one of them as f, one of them as g, and I'm going to do the math on it. So as we do that composite function, remember, we write down our first number, we leave a blank for our x value, minus 4, and I'm going to plug this entire equation in where x was, work out the math, and I get 2 times 1/2 x gives me x, 2 times 2 gives me 4, x plus 4 minus 4 gives me x. So let's work at the other direction. For g of x, I'm going to put 1/2 here. I'm going to leave a blank for this x value, plus 2, and I'm going to take my f of x and I'm going to plug it into that blank. So 1/2 times 2x gives me x. Negative 4 divided by 2 gives me 2. So I've got x minus 2 plus 2 gives me x. So mathematically, I have also verified that these two functions are inverses of each other. I got x for both of them. Okay. So really, we start saying, why are we doing this in this chapter with exponential and root functions? Because again, we are having to solve this new equation for y, right? So in this one, back here, when we swapped our x and y, it was super easy to resolve for y. We go back and we use all the tools in our tool belt. Y wants to go to the movies by himself. Like, how do we get him alone? Or, we're just trying to get him alone. In this case, we just had addition and division that we had to deal with. But as we move forward, if I had a function and I have now swapped it, and now my y is squared instead of my x being squared, I want to get y all by himself again, which means I'm going to have to take the square root of him. If my x was originally cubed, now my y is cubed. So I'm going to have to take the cube root of y to get y by itself. So again, our inverses are always those opposites. And now that we know exponents, we know that exponents and roots are the opposite side. Whenever we look at, as I like to say, PERMDAS, everything has a pair, right? So our exponents and roots have to have a pair there. Okay, so let's look at these two examples. If we have our graph y equals x squared, what is our inverse? Well, what do we know about quadratics? We know here that this is a parabola. We know that our a value is 1. We know that it starts at the origin. So I'm going to start it at the origin. My very first points are going to be up 1, over 1 for each of it. And I'm going to have my parabola. Okay. So if I have my inverse mathematically, I am going to take my y equals x squared and I'm going to swap these. So now I have x equals y squared, but I have to solve for y. So I want to get y by itself. It's squared, so I need to take the square root of y, which means I need to take the square root of the other side too. When we take the square root of something that wasn't already squared, we get a plus or minus for that. Okay, so now I've got the square root of a square. These two match, so I simply have the base underneath, and I have the square root of x values. So in the same way that I was able to make a table on this side and say that if x equals 1, y equals 1, if x equals 2, y equals 4, if x equals 3, y equals 9, and make that graph. Now, as I have folded it over, when x equals 1, y equals 1. And I'm going to use perfect squares because that's a lot easier. When x equals 4, my y is now equal to plus or minus 2. When x equals 9, my y is now plus or minus 3. So as I graph these points, when I have 1, I have 1, plus and minus. When I have 4, 1, 2, 3, 4, I've got 2, plus or minus 2. When I have 9, 5, 6, 7, 8, 9, I've got plus or minus 3. And we can make that graph. So then let's look at that along the fold test. If we were to turn it here, so I'm now vertical and I folded it in half, would that be true? So let's just work it out on here. So initially I have 1, 1, 2, 4, 1, 2, 3, 4, okay. And I have this nice parabola. Okay. And I have 4 points that I know to be true for it. I am going to fold it along my line of reflection. Okay. And maybe I'm going to fold it the other direction so that I can actually see my points here. So as I fold it, I'm going to take my pencil and I'm going to poke. If you have a hole punch, this works great too. I'm going to poke a point through there. I'm going to poke a point here. I'm poking on all of these points. That one's right on it, so I'm not going to poke on that one. And then I'm going to open it back up and see where my points land. Well, my vertex stayed the same. Those points stayed the same, and now I have 2. So let's graph it right through my poked points. Right? So now I have my original. I folded, I poked new points, and I can see that I had a vertical parabola, and now I have a horizontal parabola that lies down. Okay, so we're able to use our fold test to see what it looks like. We're also able to use our table in mathematics to tell us what it looks like. Okay, so if we looked at this one, what would the inverse of this graph be? So as we start, we've got 1/2 x cubed minus 2. So I can say right away, this is a cube root function. It's an S-curve. And so I know I've got an S-curve. I know it's not at the origin. It's been moved down to -2. And my slope for my very first 2 points is 1/2. Means I would go up 1 over 2. So my little graph's not perfect here. And then down 1 over 2 for that one. Okay? So in the same case, we're going to take our this original function here. So I have y equals 1/2 x cubed minus 3, and we're going to swap them. So now I have x equals 1/2 y cubed minus 2. And I need to solve for y. So the first thing that we do is we move our 2. We're going to move our 2 over and make it positive 2. Then I'm going to get rid of the 1/2 by multiplying both sides by 2. So now I have 2x plus 4 equals the cube root of y. Then I take the cube root of both sides. So I have y is equal to the cube root of 2x plus 4. So what does that look like? We can make ourselves a little chart and plot some points. That's a good way to do it. You can plug it into a graphing calculator or you can plug it into Desmos and see what it looks like. For that, we have a cube root function, so it's going to curve around our x-axis. So our first one was this green function. Our second one is our blue function. And just by plotting our points, and when we turn and we put our line of reflection, that mirror line in the middle, we can see that if we were to fold this, our points are identical across the line. Okay, so they're evenly folded. Our graph has reflected. So they are inverses of one another. Okay, so we checked with the fold test. We could check them with the math test by plugging f of g of x and g of f of x. Remember, they both have to equal our identity. So in the first one, I took my f of x function, and here's my little x value that I want to leave a blank for. So I did 1/2, and I left this blank, cubed minus 2, and then I take my entire g value and place it in that blank. I'm going to go ahead and set up my second one, g of f of x. Here's my x value I want to leave that blank for. So cube root of 2, I'm leaving my blank, plus 4. And I'm going to put my entire f of x value in that blank. And now we just use all the rules that we've been learning in 7.1 and 7.2 and 7.3. And we say for this one, I have a cube root and the whole thing is cubed. So those cancel each other out, and I'm simply left with what's underneath. 1/2 times 2x plus 4. This we can reduce as we distribute our 1/2 throughout our little binomial and get x plus 2 minus 2, and that gives us x. So then let's go back over here. Now everything is under the cube root, so the thing I have to do first is simplify under the cube root. So I have 2 that needs to be distributed. 2 times 1/2 gives me 1, so I have x cubed. 2 times negative 2 gives me negative 4. X cubed minus 4 plus 4. Minus 4 plus 4 cancels out to be 0, so I simply have the cube root of x cubed. I have 3, I need 3, I simply have my base. So we proved graphically that they were inverses of each other, and we also proved mathematically that they were inverses of one another. Okay, so our reminder is that as we find these inverses, we are not folding along the x-axis. We are not folding along the y-axis. We are folding along the identity equation. And the identity equation is where x equals y, where they are the same. And x equals y gives us this our basic line, that's our 45-degree line. When we turn it vertically and we shift our entire coordinate plane, then we can see that our points are truly a reflection across the line there. Now, something that's important to note is that sometimes the inverse of one function turns out to not be a function itself. And remember that the definition of a function means it has to pass that vertical line test. So let's look at this parabola that we have. Our first parabola is a function. If I take a vertical line, I can slice it anywhere along here, and it's only going to hit in one place. Now, when I reflected that parabola, I have this parabola that wraps around the y-axis. and it is not a function because everywhere I do the vertical line test, I have 2 places that it is hitting. So just because it's a function in one direction does not mean it is a function in the other direction. Here's some examples to look at. We have our line of reflection is our dotted line, our 45-degree line. We have our first line, 6x plus 4. And it is a function, our black line. And we have our inverse, where what's neat about Desmos, if you look on here, you don't have to resolve for y. You can simply write x and y in different places, and it will graph it for you. So I've got y equals 6x plus 4, and then I've got x equals 6y. I've swapped those 2 places, plus 4, and it graphed the red line. It is a function. We can see that if we turn it, that if we were to fold, we would have identical points as we moved across. Okay. Here's one where we're dealing with quadratics. So we have our line of reflection is our dotted line. Our first quadratic is a parabola, a positive parabola that faces up. It has been shifted off of the origin, and we know that because we've got extra x's and extra y's values over here. And so when we do the inverse, where we've simply swapped it, so now we've got x equals y squared minus 4y plus 3. So we're swapping out our x and our y values. That when it has graphed as this red parabola, which is not a function, because if I use my vertical line test, it's hitting in 2 places each time. However, it is the correct inverse, because when we turn and we use our line of reflection vertically, we can see that all of our points, if this folded in half, that all these points are equal, and that where it crosses, both places that it crosses is on the line of reflection. Remember, if it's crossing at any other place except along the line of reflection, we're going to have a problem. We can see out here we have another intersection, and those are identical from there. But our main center ones are crossing right there on that line of reflection. So here's an example where we have a cubic function. So the first one is this black one, and because it is a cubic function, it's going to wrap around the y-axis, and we can see that it goes in infinity here along the y-axis, and our S-curve wraps at the origin. Our second one, when we swap it, would end up being a cube root function. And so it's going to wrap and go in infinity along the x-axis. So we've just swapped them for the sake in Desmos, and then we can see if we turn it, where our line of reflection that we do have mirror. If we were to fold this in half, they would be identical. We would have our matching points go across, and they would match each other. Okay, and this is another cubic function that's just been shifted some. So we have our cube. This would be our cubic function, x cubed. This is going to be our cube root of the cube root of x function. Both of them S curves. The cubic wraps around our y-axis. Our cube root wraps around our x-axis. They cross on that line of reflection. If we rotate, we can see that they are mirror images of one another. So it's a great way to use Desmos and just switch that out and see that. So as we wrap up 7.4, we need to remember that inverse functions are just 2 functions who, when they're composite, means f of g or g of f of x, their composite functions have to equal x, which is that identity. Okay? Inverse functions are always graphed across that line of reflection. So our basic line of reflection, remember, is that 45-degree angle that we go down. To find your inverse function, you're going to swap your x and y and then solve for y again on it. So here's a couple, that's it. So that's as we wrap up 7.4 as we talk about inverse functions. For homework for 7.4, it is asking you with 16 through 24 to find the equation of the inverse relation. So like for number 16, where you have y is equal to negative 2x plus 5, if you are finding the equation, what they want you to do is actually switch these and then solve for y. So I would rewrite it as x equals negative 2y plus 5, and then I'm going to solve for y. To solve for y wants to go to the movies by himself. I'm going to get rid of the easy things first. So I've got x minus 5 equals negative 2y. Then use my division. And you can just leave it x minus 5, negative x minus 5 over 2. You could distribute that out and make it 5 minus x over 2. Either way is perfectly fine. So what you're doing with 16 through 24 is you are actually swapping them and then solving for y. So let's look at 24. 24 has y equals negative 3/7 x plus 5/7. Now, the problem that I have with this one is that I'm dealing with fractions. I don't really like to deal with fractions. So I'm going to clear that denominator first by multiplying the entire equation by a 7. So now I have 7y is equal to negative 3x plus 5 as I distribute my 7 out to each part of this, okay? So now I'm going to swap them instead and say 7x is equal to negative 3y plus 5. And I've got to solve for this y. So again, you're just going to solve for y, and it's going to give you a new answer for that. So we move our 5 over. When we change sides, we change signs. It's negative 3y, and then divide all by negative 3. You may leave it like that. You may break this out into its individual ones because the denominator goes with both of them. Either way, I'm fine with that. Okay. All right, let's see. Oh, I need a big one. For 25 through 32, it says verify that they are inverses. So what it's telling you is that the f function that they give you and the g function that they give you, they're telling you that yes, these guys are inverses. I need you to prove it to me. So the way that we prove it is to say that f of g is going to equal x, and g of f is also going to equal x. So when they give you for 25, f of x equals x plus 7 and g of x equals x minus 7, we're going to do composite. So f of g here means that I leave my space for my x, do plus 7, and I'm going to plug my g all the way into that space, x minus 7. G of f means I start with my g. I've got an x. I'm going to leave that space. Minus 7, I'm going to plug my f all the way into that space, x plus 7. And we can see that x minus 7 plus 7 gives us x, and x plus 7 minus 7 also gives us x. So we have proven that they are inverses of each other. The same is going to go for, let's do number 30. And this is why it's important to have all of our exponent rules memorized. We've got f of x is 1/3 x squared, and g of x equals 3x to the 1/2. Okay, so if I have f of g, I am going to take my f1 and I'm going to leave a space where my x is and make sure it's all the same, and I'm going to plug my entire g into that space, 3x to the 1/2. Then if I have g of f, I'm going to start writing this out. Now I've got it on the inside. I've got to make sure to keep it in the right space, all raised to the 1/2. I'm going to plug my entire f in here, 1/3 x squared. Now, this gets tricky because we have to do our steps in order. So we've got PERMDAS, right? We've got to do it in order. So our parentheses matter first, then our exponents. So in this case, I could distribute this out and then do an extra one, but I see that this is a unit. The whole thing is raised to the 1/2, so I'm going to basically call this maybe y. So I've got y to the 1/2 squared, and I have a power to a power. And a power to a power gets multiplied. 1/2 times 2 gives me 1. So I'm left with 1/3 times 3x, because my power to power here canceled out. And then 1/3 times 3 is 1, so I'm simply left with x. Okay, that's looking good. That's half of it. Now let's go over here. In this case, I am multiplied all within this parentheses, and I want to reduce parentheses first. So I'm going to do 3 times 1/3 x squared first. 3 times 1/3 gives me 1. So now I have x squared raised to the 1/2. Now I use a power to a power. 2 times 1/2 gives me 1. I simply have x. I've proven that these are inverses of one another. Okay. For 23 through 35, you are matching the graph, and that is simply using your graph form. You might want to sketch that on a different sheet of paper. If they give you a graph that looks like this, then you're going to want to turn, put your line of reflection in, and say, I need to have equal points on the side. So this one's going to go like that. They need to look like mirror images. You can turn it back, and then you can find the graph that's the same for that. So that's an easy way to work out 33 through 35 to find your inverses. On 36 through 41, it says find the inverse power function. So once again, they're wanting you to actually work it out. But now we're going to have more powers. So for 36, it tells you f of x is equal to x to the 7th. Remember, f of x is another way of writing y. I could rewrite this as y equals x to the 7th. To find the inverse, I must swap them. So I now have x is equal to y to the 7th, and I want to solve for y. How do I solve for y? It's raised to the 7th, so I need to take the 7th root. Take the 7th root. So my y is equal to the 7th root of x. It could also be written as x to the 1/7. I'm fine with either of these. Okay. If we have something like 39, where we have f of x is equal to 1/32 x to the 5th. Remember, we're rewriting this. Y equals 1/32 x to the 5th. We need to swap these. So now I have x is equal to 1/32 y to the 5th. Okay, I want to get y by itself. The first thing that I can get rid of is my 32. So I'm going to multiply by 32, and I'm going to multiply by 32 on both sides, and I've got 32x equals y to the 5th. Now, I need to take the 5th root of both sides. So I now have y is equal to the 5th root of 32 to the x. Now, in this case, this is not simplified. And I would like for you to simplify it further because 32 is 2 to the 5th. So I have 5, I need 5, this 2 can come out. So my y is equal to 2 times the 5th root of x in that case. All right, so for 42 through 47, again, it's asking you to find the inverse function. These are nonlinear, meaning that we are dealing with either a quadratic or cubic for it in the same way. So 42 gives us f of x, another way to write y, is equal to x cubed plus 2. So we're going to swap them. So I've got x is equal to y cubed plus 2 and solve for y. Move our 2, x minus 2 equals y cubed. Take a cube root of both sides. So y is equal to the cube root of x minus 2. It's perfectly fine to leave it just like that. Right? And then you have 45 to work out in that section as well. Now, for 48 through 56, it says graph this function and then use the graph to determine whether or not the inverse of f is a function. So this is not asking you to find the inverse, it's just asking you to graph it and then decide. So for 48 tells us f of x equals negative 2x plus 3. Something that I'm going to tell you is that we need to know what the graph is. This graph right here, x is raised to the 1, so it's a line. Every line, unless it starts out as a horizontal line, so then our inverse is going to be different, is going to be a function. So I've got some line with a negative 2 slope. If I'm doing my vertical and I'm swapping it over, I'm going to have this other line here. It's going to be a function. They actually both have negative slopes in this case. But the first one is a function. So as we answered that question for 48, you would just say, yes, it's a function. Okay. So then let's look at maybe 51. 50 and 51 give us an equation where our f of x or our y is equal to x squared plus 1, or as in 51, negative 3x squared. So these are these are quadratic functions. So we already know that they're a parabola. This is a parabola that faces up. This is a parabola that faces down. When we inverse a parabola, it's going to be a horizontal parabola every single time. Either that way, actually this one would face that way. So when we inverse a parabola, it's not a function because it's hitting in multiple places. So you would say no, not a function. And again, you are welcome to use Desmos to graph these so that you can see the difference. Remember, when you plug them in on Desmos, if you were plugging in 50, I would plug in my first equation as y equals x squared plus 1. And my second equation, I'd plug in as x equals y squared plus 1, and just let it graph both of those, and it will graph those functions for you. So that's the difference of inverse functions in class, and also on our Google Classroom, I have hole punch templates, and they look like this. And so we will learn to write the equation of the graph. In this case, it's a linear equation. The way this works is that we're going to fold it directly on our line of reflection on this dotted line. We're going to fold it down, punch through each point using a hole punch or a sharp pencil. Either way, punch through these. Watch your finger on the back side. Okay. We're going to unfold it. Notice that it crosses at the line a reflection. Oh, if I missed that one, it would go right there. And then we're going to graph our new line. So our new line is going to go through all of the parts that we just hole punched. So my equation for this line, I know that my y, I have an intercept, right? So what's my slope? Up 2 over 1, so 2x, 1, 2, 3, 4, minus 4 is my first line. Let's look at my second line. Y is equal, my slope is up 1 over 2, so 1/2 x plus 2. So we're able to write our equations, and then these two equations we can mathematically prove are inverses of each other. So there's some linear ones, and there are also some quadratic ones that we're going to work through in class, figure those out. But these are also posted for you to use again and to be able to fold and use your hole punch and see how these are inverses of one another.